Hey everybody, we're going to be looking at Chapter 10, Organohalides and alkyl halides in this chapter. You should have already started Chapter 10, so we're just going to kind of continue on. I'm going to do a little bit of review and then we're going to look at the rest of Chapter 10. So the first thing that we want to look at today is the idea of allylic bromination. And so allylic does mean that there is an alkene, and so we're going to be taking an alkene and turning it into this halogenated type of alkene. So remember from earlier chapters, we talked about this idea of having an alkene, and we added HX. So in this case, since we're talking about bromination, it would be HBr. And from there, we would make an alkyl halide. And remember that this is a Markovnikov type of reaction. So the X is going to go to the more substituted carbon, the H goes to the less substituted. But for allylic bromination, we're specifically looking at an alkene with NBS. And so again, you don't have to know exactly what the structure of NBS is, but you should obviously be aware that the B stands for bromo. So that's where our bromine is coming from. And we also need to react it with some light. And so we represent light as H nu, which you might remember from general chemistry, means Planck's constant and frequency. And then we could put it in some kind of solvent like carbon tetrachloride, put that all together, and we'll end up with this allylic bromine or bromide. So what the heck does allylic even mean? Let's look at just a general alkene just to start off with. So remember in an earlier chapter we looked at these two carbons, the carbons that are directly attached to the double bond, and those were called vinylic carbons. And so the new ones that we're going to look at, the allylic carbons, are one carbon away from that double bond. So the red in this case is allylic. Okay, so we have vinylic directly on, allylic is one away. So let's look at an example with just general cyclohexene. We're going to add our NBS, some light, and again, let's look at where our allylic locations are. So we have one here and one here. And in this case, we can see that it's symmetrical. So it doesn't matter where the bromine goes, it's going to create the same compound. So for our final structure, the alkene doesn't go anywhere. We're still going to have that double bond, but now we have the bromine in that allylic position. Now this does happen through a radical chain reaction, and we looked at radical reactions earlier. I believe it was in chapter 6. So let's talk a little bit about this allylic radical. So our allylic radical is very stable, and the reason that it's so stable is due to residence. So an allylic radical, let's just say, for instance, we have this. So remember, a radical means that we are looking at one lone electron, an unpaired electron, in the allylic position. This is our allylic radical. So what can happen through resonance is we'll see one of our electrons from our double bond moving over, and our electron from our radical moving over. The other electron from our bond moves over, and so we end up with this resonance form. Okay. So we end up with a lot of resonance because that unpaired electron is delocalized. That's what we call it, a delocalized electron, because it can move around wherever it needs to go in order to be more stable. So if we're looking at a product that is unsymmetrical, so unlike the one that we saw before, unlike this example that I just drew, we're going to see two products because it's going to have two different radical intermediates. So let's say, for example, that we're looking at this compound. So we have this double bond here. Now in this case, we only have one allylic position based on what we just originally saw. We know that that's going to be our allylic spot. So we expect our radical to look like this, right? But we know that through resonance, we can switch it around. So our resonance structure, if we draw the arrow pushing, our arrow goes there, one of the electrons from our bond goes here, and the other electron goes here. So that gives us a second possible intermediate. So now our double bond is here, and we have our radical here. So these are our two possibilities. So then we can look at what our actual products could be. So here, again, the bromine is going to go in that allylic spot. So our bromine would go here. Or we will also make this compound. So we have two different possibilities here. But this compound on the right is going to be our major product because there is less hindrance. In other words, there's more room for that bromine to go in. Because remember, bromine is a pretty big atom compared to a carbon. So it needs its space. It wants to be on the end. So here, if you're looking at an asymmetrical type of compound, you have to be able to draw both possible products. So just to make sure that everything is clear, let's look at all of the different types of radicals that we can come in contact with. So the first one is vinylic. That is our least stable. So remember, vinylic is part of a double bond. It is directly on that double bond. So this is called vinylic. It is the least stable radical. So then our next radical is going to be a methyl radical, where we have CH3 and our lone electron. So this is called methyl. Vinylic and methyl are really actually very close in stability, but vinylic is a little bit less stable. So after methyl, we're going to have primary, which means there's one other group on there. Then obviously secondary comes next. So we have two groups. And so I just put R prime just to say that it could be a different R. It doesn't have to be the same R. And then obviously we can have tertiary. So R, R prime, and R double prime. And then our most stable version is our allylic. I ran out of room, so I'm going to draw it down here. So for allylic, we're looking at something like this. And that's going to be our most stable radical. Now, why does it even matter that we're able to do this, that we're able to use this allylic radical, that we can do this type of bromination? Well, it's helpful for us in making dienes. So we looked at some examples of dienes before, but we never actually looked at how they're synthesized. And so here, if we look at our original version with the cyclohexene, we started with this. We added some NBS with light. We made this compound. Now remember, we can undergo a dehydrohalogenation. And we looked at that in chapter 8, where we have an alkyl halide and we can add a strong base. So something like NaOH or KOH, just some strong base, and here we'll make an alkene. So in this case, we already have one alkene. So if we add our strong base to undergo the dehydrohalogenation, we're going to end up with 2 alkenes now. So now we have made a diene as our product. So NBS, making this allylic bromine, can be a useful intermediate for us. Let's look at another type of reaction. And so for our next one, we are going to take some alcohols and we are going to make alkyl halides. So we're going to go from alcohol to alkyl halide. And what you use for your reactant depends on what type of alcohol you have. So if you have a tertiary alcohol, so tertiary, again, meaning you can have, if this is your carbon, you have your alcohol group, and then you have 3 different groups. They can be the same group, but we need at least carbons. We can't have hydrogens, right? So we need 3 different groups with our OH. If we have a tertiary alcohol, we can use simply HX. And we'll see a substitution where that alcohol will get kicked off and we'll make our alkyl halide. So, in the case of what we have here, our alkyl halide would be CX and then all of our R's. So everything else stays the same, except we're kicking off that OH and we're adding that X. So that means that our other product here is going to be water. So if you see a tertiary alcohol, you're going to add HX to make an alkyl halide and water. For primary or secondary alcohols, we use something different. So for a primary alcohol or a secondary alcohol, we can use 2 different options depending on what we want. If we want to add chlorine, we're going to add this thionyl chloride. Which is SOCl2. So if we want to add a chlorine, we're obviously going to add SOCl2. Our other products for this reaction will then be sulfur dioxide and hydrochloric acid. So again, once you make your product, all we're doing is kicking out our OH and adding a chlorine in there. But the other products we will make are SO2 and HCl. If we want to end up with a bromine, we are going to add phosphorus tribromide. So that is PBr3. And in this case, besides making our alkyl halide, we're also going to make some phosphoric acid. Oops, I'm sorry, that's not correct. It should be phosphorus acid, PO3. There we go. All right, so those are the options if we want to add a chlorine or a bromine if we're looking at different types of alcohols. So tertiary, you would use HCl or HBr. Primary or secondary, you would use thionyl chloride or phosphorus tribromide, depending on what halogen you want. It's possible for us to make alkyl halides, They're pretty unstable, so it's not likely that it could happen. But for an alkyl fluoride, you would add HF, specifically in the solvent pyridine, and that will make an alkyl fluoride. But again, pretty unlikely that you'll see that happening. So we've looked at allylic bromination, dehydrohalogenation to form a diene, making alkyl halides from alcohols. And so our next topic is looking at something called a Grignard reagent. And we saw something kind of similar to Grignard reagents earlier in the semester. I believe it was in chapter 8 or 9, where we added lithium into our solutions. So a Grignard reagent is when we have Rx, so that's an alkyl halide. Remember, R could be anything, X is our halogen, reacts with magnesium. So a Grignard reagent is always going to have magnesium in it. And that magnesium is usually going to be in ether or tetrahydrofuran, THF, and it'll make the Grignard reagent. So your Grignard reagent is going to be RMGX. So just like what we saw with the lithium goes in between the carbon and the halogen. Same thing here. Our magnesium goes in between. So this creates an organometallic compound. Oh my. We'll just cross that out. So an organometallic compound, the organo means obviously that it's organic, and the metallic means that we have a metal there. So because we have that magnesium with the carbon, we make organometallic compound. So here, this is important because this is a very polarized bond. If this R is a carbon, we expect for our dipole moment to be going towards the magnesium. Sorry, I said that wrong. We expect for our dipole moment to be going towards the carbon. I can't erase that, so we're just going to start over. If we have carbon and magnesium together, our dipole moment will go toward the carbon because magnesium is going to have a lower electronegativity, so it's going to be our partial positive. Carbon's going to be our partial negative. Sorry about that mix-up. So here we are creating something called a carbanion. And so carbanions are now going to be very good nucleophiles, right? They have that partial negative charge. They're going to attack, and it's going to also create a strong base. So this carbon-magnesium bond is highly basic, which means that these particular types of reagents, these Grignard reagents, are very sensitive to moisture. So when we're first making a Grignard reagent, we have to be really careful that we don't have any moisture allowed in the system. But then once we have our Grignard reagent, so let's have our CMGX. Once we have that Grignard reagent there, we can add water, and that's going to kick off the MGX so that we end up with an alcohol. So of course we know there's other stuff coming off that carbon, but this creates an alcohol, and then we're left with MGX2. Okay. So we use Grignard reagents when we want to go from alkyl halides to an alcohol. So we looked before at going from an alcohol to an alkyl halide. This is our reverse. Now, generally speaking, we expect for chlorine to be less reactive as our halogen than bromine or iodine. And we're going to talk about why in chapter 11. Active than So now let's look at organometallic coupling reactions. So this is going to be similar to what we see with our Grignard reagent, but in this case, we're going to use lithium. So for our next topic, we're going to look at an organometallic coupling reaction. So here we can make an alkyl lithium. This is the same idea as a Grignard reagent, but it has lithium instead of magnesium. So we call that RLI instead of having the RMGX. So just like the Grignard reagent, all organometallic compounds are going to be highly nucleophilic and it's going to be a strong base. So in order for us to make this type of compound, we're going to start off with our RLI compound, and we specifically need 2 of them. And from here, we're going to add some copper 1 iodide in ether. Through this process, we're going to make a compound that is LiR2Cu. This particular compound is called a Gilman reagent. And the whole reason we're doing this, the whole reason we're trying to make a Gilman reagent is because we can then add the Gilman reagent to another hydrocarbon in order to make a longer chain. So here all we're doing is taking one hydrocarbon and we're trying to elongate it. So let's say, for instance, that I'm starting off with, let's say CH3Li. So technically our H's are over here and our Li is attached here. So we're going to add CuI. We don't need to worry about the mechanism for this reaction. We're going to run this reaction in ether. And so we're going to end up with Li, 2 of the R's, so CH3, 2, and Cu. This is our Gilman reagent. So now what we can do is add our Gilman to an alkyl halide and make an elongated hydrocarbon. So this is another example of why we tend to use these organometallic compounds, why they're important for us. So here, let's say we have our Gilman reactant. So we have LiCH3 2 with copper, and we want to add on to this compound. So we have an iodide compound here. We're going to put that in ether again. And now we're going to end up taking one of these CH3 groups and replacing it with that iodide. So this had 1, 2, 3, 4, 5 carbons. So now it's going to have 1, 2, 3, 4, 5, 6 carbons. So all we did was take off that iodine and throw on that CH3. That means we're also going to have lithium iodide as a product, and we're going to have CH3 left because we only used one of them attached to copper. So this is a case that's very simplistic. We're just using a methyl group, Let's look at one that's a little bit more complex. Let's say we have this as our Gilman reactant. So here we have what would be a propyl group. And we're going to add it to this compound. So we have 1, 2, 3, 4, 5, 6, 7, 8 carbons here. And we're going to add 3 more carbons because we're only going to add one of them, right? So our product, if we run this in ether, is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That is our new final product, plus lithium chloride, plus C3H7Cu. So again, all we're doing is elongating. Now it's possible that instead of having the chlorine at the very end, having a terminal chlorine, I could have a chlorine somewhere like here, which just means, again, that's where our group would change. So in that case, we would have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So our 8 carbon chain, would still stay the same. Oops, I did too many. 1, 2, 3, 4, 5, 6, 7, 8. There we go. And then instead of the chlorine, we would add that propane. So that's going to be 1, 2, 3. Okay, and I did it in the wrong spot because I'm a mess right now. That would have been here, not here. Sorry about that, guys. But hopefully you're getting the gist that depending on wherever that halogen is, that is where you're going to attach your carbon group. So then our last piece of chapter 10 is looking at oxidation and reduction. And we already kind of looked at this a little bit in our different types of reactions like oxidative cleavage and things like that. But again, let's just remind ourselves that oxidation means that we are either forming a bond that is going to be carbon oxygen, carbon nitrogen, or a carbon halogen, or it breaks a CH bond, which could mean, in that case, that it's turning into a multiple bond, like an alkene or an alkyne. So then reduction, of course, is the opposite. Here we are breaking CO and CX, and we are forming CH bonds. So in this case, we could be going from an alkyne to an alkene or an alkene to an alkane. We're getting rid of those multiple bonds. So, for example, if we had something like methane, and we add chlorine, we're going to end up with our alkyl halide plus HCl. So in this case, we broke a CH bond. We broke this bond right here, and we formed a CX bond. So in this particular case, this is an oxidation. But if we look at this other example, we could have something like this carbon, ethylene, and we add something like HBr, and we make an alkyl halide. So in this case, we can see that we are adding a CH bond. And when we add a CH bond, that is reduction, but we're also adding a CX bond, which we know is oxidation. So here it's a wash. We have an oxidation and a reduction occurring. So here we would say overall, this is neither a reduction or an oxidation between these two materials. So as a general rule, the more multiple bonds that you have, the more oxidated it becomes. So just to kind of wrap everything up, we can look at if we have, for instance, hydrocarbons. So for hydrocarbons, we could have something as simple as a CC bond. It'll become more oxidized if we have a CC double bond, and then more oxidized if we have a CC triple bond. If we have a carbon with an oxygen, obviously having an alcohol is the lowest oxidation. Then we can have a ketone is next. Then we can have a carboxylic acid is our next highest oxidation, and we can get oxidized all the way up to carbon dioxide. With a halogen, we can start off as CH3 with one X, add another X, add another X, until eventually all we have are X's and no hydrogens. And then if we're looking at compounds with nitrogen, we can have CH3NH2, then create a double bond, H2C and H, and then create a triple bond, HC triple bond to N. So again, the whole purpose here is starting with low oxidation, and we're becoming more oxidized as we move from left to right on this list. Now, the way that I drew this list doesn't mean, oh, well, nitrogen's at the bottom, so it's the most highly oxidized. That I'm not drawing anything from top to bottom. We're just looking from left to right and comparing compounds in their own right. Okay, so that is the end of chapter 10. Thanks so much.